In the video for exercise 313, we talked about the first of four factors that you want to consider when you're comparing two acids qualitatively, and you want to figure out which one is the strongest one. You don't have Ka values, you don't have pKa values available to you, so you can only use a rule of thumb, a qualitative rule of thumb, four factors that will tell you which hydrogen is more acidic, which hydrogen is more likely to come off of a molecule. And the first and most important factor was the atom. We saw in the previous video that if a hydrogen is on two different atoms, if those atoms are in the same column, then the atom that's further down will be more acidic, and if the two atoms that hydrogens are on are in the same row, then the one further to the right will be more acidic. If the two hydrogens you're comparing are on the same type of atom, so they're both on an oxygen, or they're both on a carbon, then you want to look at a second factor, and that second factor is resonance. So the hydrogen, that leaves behind more resonance is more acidic. So for example, if you had two molecules here, let's say we had these two, and we want to consider which hydrogen is more acidic, this one in orange or this one in blue. The procedure we'd follow is the same one we followed for an atom. Let's say the hydrogen comes off. If that hydrogen leaves and doesn't take any electrons with it, then it's going to have a positive charge. The bond, the electrons that were in the bond, are going to become a negative charge. Same thing for the other molecule. If the hydrogen leaves, it doesn't take any electrons with it. If it's an acid, it leaves as an H+, and the electrons in the bond become a lone pair on that atom. And so the question is, which of those two molecules is more stable? The one that's more stable will let the H get away. And if one is less stable, it won't be able to handle its negative charge, and it'll snatch back the H. And the H won't be able to get away, and it won't be able to behave like an acid. So which of these two is more stable? Well, you'll notice that that lone pair is a allylic. It's one atom away from an atom in a double bond. And that means that you have resonance there. This lone pair, if you wanted to draw the other resonance structure, you could draw something like this. And the idea with those resonance structures is that the true molecule is something like this, with a slight negative charge on the two end carbons. There's no resonance associated with the structure on the right. And so compare. The structure that has resonance was able to spread out the charge. That made the charge smaller at any individual place. This is only a partial negative charge, as opposed to a full negative charge. That means that the negative charge doesn't repel itself as much. It's sort of like diluting it, spreading it out over more space, and so it's more stable. As opposed to this molecule in blue, that molecule, that negative charge is stuck on one atom. It's a full negative charge stuck in a small space. It repels itself. It can't handle the negative charge. It sticks to any positive thing near it. That's going to be the hydrogen. And so it wouldn't let that hydrogen get away. It would stick right back to it. Those two electrons would become a bond again. So because the resonance structure is stable, the hydrogen can get away. What does this care? It's able to stabilize its charge. It's fine. The hydrogen can leave, and so the original molecule is able to give away a hydrogen. In other words, it's able to act as an acid. Whereas the structure that didn't have resonance was too unstable when the hydrogen left. And so it was not able to act as an acid. It was a weaker acid. So the hydrogen that leaves behind more resonance, in our previous example, that was the orange one, that hydrogen will be able to come off the molecule more. That hydrogen will be more acidic. So in exercise 315, that's the thought process we're going through. Let me draw the two scenarios here. So if we have this molecule with, let's say, the two hydrogens, and actually, let me do these colors. So let's say you have this blue hydrogen here and the red hydrogen here. So imagine that the hydrogens do come off. We'll imagine that separately. So first, imagine the blue hydrogen comes off, doesn't take the electrons with it, it leaves as an H+, as an acid, and the electrons that were there become a lone pair. Then imagine the red hydrogen comes off, doesn't take the electrons with it, it's leaving as an acid, an H+, and it leaves behind its lone pair. So which of these molecules is more stable? Because this lone pair is allylic, it's one atom away from that atom in a double bond, it's going to be involved in resonance, and the negative charge will be spread out. The electrons will spread out, and the negative charge will be partial over here and partial over there. That stabilizes that molecule. Whereas on the right, this is not allylic, this lone pair is not allylic, it's 2 atoms away from an atom in a double bond. So it's not allylic, and so this lone pair and that negative charge is stuck just on this one carbon atom, very unstable, and so it just snatches the hydrogen back. Hydrogen isn't able to leave, and so that molecule, that hydrogen isn't able to act as an acid. So the more acidic hydrogen here is the blue one, because it leaves behind more resonance. Okay, we can use that same thought process for the rest of these. If this hydrogen were to leave, let's imagine that hydrogen leaving, so let's say it goes off into solution, the electrons in the bond will become a new lone pair. And that lone pair will bring a negative charge with it. Then imagine the other hydrogen leaving. It pops off the molecule, and the lone pairs that are in that bond, the electrons in that bond become a lone pair on that nitrogen. Now there was another lone pair on each of these nitrogens that weren't being drawn before, so that nitrogen also, the one on the left, has a negative charge. So the question is, which negative charge would be more stable? And the negative charge that would be more stable is the blue one, because this lone pair with the negative charge is 1 atom away from an atom in a double bond, so it's going to be involved in resonance. It would go toward the double bond would go to become a new lone pair. And so the negative charge would get spread out over more atoms. Whereas the lone pair on this nitrogen on the left, the red one, that's not 1 atom away from an atom in a double bond. So that's not involved in resonance, it's localized, it's stuck on that one nitrogen, so that makes it very unstable. So the more stable, the more acidic hydrogen is the one that leaves behind more resonance, and here that was the blue one. For C, you can play a similar game. Let's say this blue hydrogen left. Then the electrons in that bond would end up becoming a lone pair. I'll draw those in as blue dots. And then let's compare if the red hydrogen left. The electrons in that bond would become a lone pair. Both of these lone pairs would have a negative charge, and the question is, which one is more stable? And it's the red one, because this negative charge, that lone pair, is 1 atom away from double bonds in 2 places. So it's going to have a lot of resonance. It's really going to spread that negative charge out. Instead of being a full negative charge in one place, these electrons can go here, in which case the lone pair would go there, and that would be slightly negative. Or they could go here, and the lone pairs would go there, and that would be slightly negative. And so this wouldn't be full negative, it would be slightly negative. In other words, because there's so much resonance, the charge gets to spread out all over the molecule, and that helps to stabilize it. Whereas in the blue one, this is not one atom away from a double bond, it's on an atom in a double bond. So this is not involved in resonance. And so the charge is stuck in one atom. That makes it very unstable. And so it just steals the hydrogen right back. It's the other one, the red hydrogen, that's able to come off because the charge it leaves behind is stabilized through resonance. Okay, without drawing those lone pairs over and over again, we can see very quickly which hydrogen will leave behind more resonance. Because this hydrogen here, the lone pairs will be on this atom, that's one atom away from an atom in a double bond. So that's going to leave behind resonance. Whereas for the blue hydrogen, the lone pairs would be here, that's 2 atoms away from an atom in a double bond. That's not going to be involved in resonance. And so the red hydrogen here is going to leave behind more resonance, and that resonance will spread the negative charge out and stabilize the molecule. Now E is just reminding you that you always have these 4 patterns, and the most important one is at the top. Whenever you look at a molecule, always ask yourself if the hydrogens are on different atoms, different types of atoms. Only if they're on the same type of atom would you ever consider resonance. Now, there are definitely exceptions to this rule. This REO is a rule of thumb. But on a test, I'm not going to give you the exceptions. I'm going to give you the things that follow this rule. So always consider the atom first. Only if the two atoms that the hydrogens are on are the same would you go to the resonance. And so in E, it's just bringing that home. You have these 2 hydrogens. If you were just looking at resonance, you would notice that both of the hydrogens are allylic, or they would leave behind allylic lone pairs. But that doesn't matter here, because the red hydrogen is on a carbon, and the blue hydrogen is on an oxygen. Those are different types of atoms. Carbon and oxygen are in the same row of the periodic table, row 2. All right. So you'd have carbon, and then there's nitrogen, and then there's oxygen, and then there's fluorine, sort of in the top right of the periodic table. So they're in the same row, and our rule for an atom was, in a row, hydrogen on an atom further to the right is more acidic. So here, the oxygen is further to the right, and so the hydrogen on the oxygen is more acidic. And the reason for that is because in rows, the most effective thing is the electronegativity. Oxygen is more electronegative. That means that it takes the negative charge that it has to stabilize and it pulls it closer to the nucleus. That's what it means to be electronegative. It pulls electrons close to the nucleus where there's positive charge, and so that helps to stabilize the negative charge more. Whereas with carbon, carbon's not as electronegative. It has the negative charge. If it has a negative charge, it isn't able to bring it as close to the nucleus because it's not as electronegative, and so it doesn't stabilize it as much. So the hydrogen on the oxygen is the most acidic hydrogen of those 2. And F is really asking the same thing. Yet again, we have a carbon bonded to the hydrogen and an oxygen bonded to the hydrogen. And so through the same reasoning, those are in the same row. If elements are in the same row, the hydrogen bonded to the element that's further to the right in the row is more acidic, so this hydrogen is more acidic. And that's because when it leaves behind that negative charge, and the oxygen is better able to stabilize the negative charge with its electronegativity. It pulls the electrons with the negative charge closer to the nucleus, where there's all that positive charge to help to neutralize it. It pulls electrons to the nucleus more effectively than carbon does, and so it helps to neutralize those electrons better or more effectively than carbon does. So that's just a little bit of practice for how you can use resonance as a guide for determining the stability of a molecule the stability of the charge that's left behind when a H plus leaves a molecule. And that lets you determine how likely that hydrogen is to leave. If what it leaves behind is stable, then it's definitely going to leave. And that makes the hydrogen more acidic, because that means that the molecule can donate that hydrogen to solution more often, which is the definition, the Bronsted-Lowry definition of an acid.